With me today is Johnny Dorigo Jones. Johnny is a PhD candidate at CU Boulder in the Astrophysical and Planetary Sciences Department. He's published multiple papers on different topics in astrophysics, and among other interesting projects, his current research focuses on applying machine learning algorithms to better understand the physics of the early universe.
How's it going, Hunter? Looking forward.
I'm very excited to dive into this with you.
Awesome.
Great. Let's start off with the Big Bang.
Mm-hmm.
So the Big Bang is like the very beginning of everything in the universe, right? It's often misunderstood to be some big explosion that happened, but that's not exactly it. It's the expansion of space. Kind of, I think of it like if you were to blow air into a balloon and that balloon just keeps growing and growing and growing. You can think of the universe that way, and the Big Bang just starting from this really small point. Everything in the universe could fit in your hand, and then at some point something just made that start rapidly expanding in size, and it's still happening today. The universe is still expanding, and there's a lot of stuff we don't know about that yet. So now, beginning of the Big Bang, there's just this hot soup of energy, but eventually it cools down, and that allows the formation of matter, and that's where your research comes in. Is that correct?
Yeah, absolutely. Yeah, that's when neutral hydrogen started to form after the Big Bang.
So what is neutral hydrogen?
Neutral hydrogen is just a proton and an electron that are bound together. It was the first element that ever formed, and then helium formed shortly after, and then all the other elements came way later after stars already formed.
Okay, so neutral hydrogen is matter. It is the very first piece of matter that ever
Correct.
formed in the universe. Yep. At this point in the universe, hydrogen is the only matter that exists.
Yep, just that and photons.
So, why is neutral hydrogen important to the history of the universe?
Yeah, so you mentioned it. The Big Bang happened, and then space-time formed, and then once it expanded enough, then photons were able to stream freely, and that happened when neutral hydrogen formed. So you can sort of think about it as like the density sort of went down. It was no longer this super dense material. We had hydrogen atoms, and then that's what formed the cosmic microwave background. So that's sort of the baby picture of the universe when photons were able to travel freely for the first time and reach us here at the present day.
So when you say that photons are traveling freely, you mean that's like there's just kind of darkness before, and now all of a sudden like hydrogen is like shining a flashlight around, right? And
That's
so
great.
We can see light now in the universe.
Yeah, exactly.
And how big is the universe at this time?
Well, yeah, when it first formed, about the size of an atom, but after that, probably still smaller than a galaxy, I would guess, until the Dark Ages.
Interesting.
That's
Okay.
just a complete guess, though.
Yeah, it's okay. So now we've reached the cosmic Dark Ages.
Yes.
And so the universe is full of neutral hydrogen, but there's no stars yet. Light is shining, but it's not actually a lot of light, is it? There's only one specific type of light that's shining right now.
That's right, yeah. So neutral hydrogen emits at the radio wavelengths, so really long wavelengths, and that's what the 21 centimeter signal is.
Okay, so this 21 centimeters is how long the wave of this hydrogen is.
Mm-hmm.
And that 21 centimeter signal is the only light that's coming from the
Right,
universe.
that's just, if neutral hydrogen exists, then the 21 centimeter signal will be emitted, but yeah, it takes much longer for stars and galaxies to form for us to get ultraviolet light, X-rays, and all that fun stuff.
So it's dark, it's silent, but it's not empty. It's full of this neutral hydrogen. There's maybe a little bit of helium in there as well.
Yeah.
There's just this one piece of light that's being emitted. So how do we know this?
Mainly just from our theoretical understanding of atoms and, this transition in neutral hydrogen. We're still trying to observe this cosmological 21 centimeter signal. There's some tentative detections. Also just from being able to observe the 21 centimeter signal at lower redshift, so in nearby galaxies we can observe its emission. We're pretty sure that if it existed in the very early universe, it will be emitting this signal. And there's so much neutral hydrogen that we're expecting to be able to observe it, even though it's a fairly faint signal.
I've heard you say the word redshift. Redshift is happening because the universe is expanding. So every type of light has a certain wavelength. And as the universe stretches, that wave is getting longer. It's kind of like drawing a little stick figure on a balloon, to use that analogy again. It's like drawing a stick figure on a balloon and blowing it up. The stick figure gets bigger and it gets stretched. As it gets stretched, it becomes redder, right? And so we experience something like this every day. When cars drive by us, you can hear a car coming towards us, and as it comes towards us, the pitch in its sound gets higher. It goes, meow, and then as it passes us, the pitch gets lower. The exact same thing is happening with sound waves when cars are coming by. The wavelength as it travels towards us is getting shorter, but as it's going away from us, it's getting longer. So light does the same thing as sound. As light is coming towards us, it appears bluer, but as it's getting away from us, it appears more red. So we can actually use that as a tool to calculate how far away something is. Is that correct? Yep. So that is how redshift is distance, because the redder something appears, the more far away it is in general.
Yep.
So how do we detect this neutral hydrogen?
Yeah, so it's definitely involved with redshift. So 21 centimeters, the rest wavelength that it's emitted at. But as it reaches us, that goes to much longer wavelengths, up to feet or meters. And because it's in the radio, you need radio telescopes, so radio antennae. And the reason the far side of the moon is involved in detecting the 21 centimeter signal, we're on the radio here. There's all FM and AM radio signals from literally everything on Earth. So the whole idea is that we want to escape that radio frequency interference, go to the most radio quiet part of the solar system, which is the far side of the moon, and set up radio interferometers there, which is what my advisor's been trying to do for his career.
There's a lot of hurdles you have to jump through.
There's multiple. We haven't even gotten into the hardest ones. Yeah.
In the universe, let's get back to our timeline. We've had the Big Bang, and then the very first light emitted, and now we've been talking about this neutral hydrogen. No stars are forming yet. But yeah, let's get into the age of stars.
Yeah, maybe that's confusing, saying like photons are able to stream freely, and that was maybe technically first light, but then it's then the stars and galaxies form. So that's the first actual light emitted from astrophysical objects, right?
Okay, yeah.
So that's a little confusing.
So at the very beginning, there was just this 21 centimeter line of light being emitted. That's not something that humans could see. It's a very faint source of light.
Yep.
So now we're going into the first light when the very first stars are being born. The very first stars ignite and they light up the universe. Galaxies begin to form. Can you tell us a little bit about this period?
Yeah, exactly. So it just took a long time for all of this gas in the universe to condense under gravitational pressure and energy to form the first galaxies, the first supermassive black holes, the first stars. We're not exactly sure which of those formed first. But yeah, so large-scale structure began to form. The intergalactic medium came about, which is just that space between galaxies. You can think of it as threads between different galaxy clusters. And that's all neutral hydrogen, and that began to collapse and form the first structures in the universe. And one of the big questions, which we might get to later, is JWST is starting to observe the first stars and galaxies about redshift of 15 or so, and they're seeing that they're larger than they expect them to be. And so one of the big questions is, did the first supermassive black holes form before galaxies even, in order to get those very massive galaxies? And that's one of the things that we could potentially probe with the 21 centimeter line.
You're looking at redshift 30, is that what you said?
That's when the first stars and galaxies formed.
Okay, so the higher the redshift, the further away, right? Yeah. So is there some type of grounding we could have? What is redshift 1? How far away is
redshift 0 is where we are at right now. Redshift of 1 is, considered the local universe. That used to be considered very far away, but now with all these advanced telescopes, we can see to super high redshifts. So it's sort of making the universe smaller. But the CMB, the cosmic microwave background, the baby picture of the universe, that was redshift of 1100.
That's the furthest that we can see is. So the cosmic microwave background is the very first light that was ever emitted from the universe. Is that 21 centimeter line, or is that different?
That's different. So the cosmic microwave background is essentially an understanding of the fluctuations in the matter density of the early universe. It's a really faint signal because the universe was essentially uniform and isotropic at that time. Yeah, that was one of the first really big astrophysical detections, was the cosmic microwave background by Penzias and Wilson, I think. And they first thought that detection was bird poop in their telescopes, and then they figured out, no, we're actually seeing something. And so when you look at a TV screen, the fuzzy black and white, some of that is the cosmic microwave background, actually.
We're actually able to see that.
Right, yeah,
and it's the same with radio static, right, too. Yeah. So if you're tuning your radio in your car, if it was 20 years ago,
Mhm.
and you hear that static, that you were hearing the very first
Yeah.
light being emitted.
Yeah, that
from
and
the
also
universe.
probably cosmic rays in our atmosphere and stuff
Yeah.
like that. But
Yeah, you could be your very own astronomer in your own home
absolutely.
with just a TV, and you could see the very first light from the universe. So we now have our first stars that were ignited from this hydrogen and helium collapsing in on itself so tightly that it started to ignite and heat up. And so those stars would group together, they'd form galaxies. Galaxies can group together and they can form galaxy clusters.
Mhm.
And so now the universe is starting to look like how we know it
Yep.
as today. And how much time has passed at this point?
Yeah, so it was about 100 million years from the Big Bang to those first stars and galaxies.
100 million years, cosmologically, is not
Blink
that
of-
long.
blink of the eye,
Yeah. But for us, it's
Yep.
the longest thing that we could imagine. But yeah, so this is very, very fast. How old is the universe? 13.8 billion years?
Yeah, about
Is that-
13.8. Yeah.
So yeah, 100 million is nothing compared
Yeah,
to
it's a
13.8.
fraction,
Yeah. So this is happening pretty quickly relative to the age of the universe. So the structure of the modern universe is made of galaxies, stars, and as you said, black holes.
Mhm.
And we are somewhere in this mess.
We're not really sure what the first galaxies look like. Like
Yeah.
maybe they looked like the present day galaxies, but maybe there were completely different types of structures. Like
Mhm.
maybe they were just supermassive black holes that were surrounded by like some small amount of this neutral hydrogen gas. Because like these like grand design spiral galaxies that you think about when you look at like the Hubble images or whatever, those probably didn't exist in that like form at the very early universe. It probably took some time for those really nice large types of galaxies to come
that's very
about.
interesting.
Yeah.
And so then galaxies eventually evolved to
Yeah.
be what we see them as. And so we are in the Milky Way, somewhere in an incountable amount of galaxies in the universe. In the Milky Way, there's about 100 to 200 billion
Something like that,
stars inside, and we are just one of those
Right.
stars.
Yeah. And we have almost all of them mapped. There's been some really cool satellites recently. One called Gaia that I used in my first research project.
And then within that, the stars that we see in the sky are only like a very small portion of the neighborhood
Right.
inside of the Milky Way that
Yeah.
we see. We don't really see many things
Mhm.
outside of our galaxy. We could see the Andromeda galaxy, which
Mhm.
is our largest neighbor.
Yeah,
If
that's
you're
the
in a really
farthest-
dark spot.
Yeah, that's probably the farthest thing you can see with the naked eye.
Yeah. So we see a very small fraction of the stars,
Yeah,
even in the
exactly.
Milky Way. We are one of those stars, and our star was lucky enough to have a planet that is orbiting it at just the perfect distance for water to be a
Goldilocks zone.
liquid. Yes.
Yeah.
Yes, and somehow life formed at that
Somehow.
at some point,
Yeah,
and we don't entirely know, and we're trying to figure that out, and we're trying to see if life exists somewhere else in the universe too.
exactly.
And a lot of the research you do is very quantitative. It's very analytical, but you can't help to just imagine like
Oh yeah,
philosophical.
exoplanets is a massive. It's probably the most popular field right now in astronomy, just in general. Because like we have ways to measure the chemistry of nearby exoplanets, and that's really how you can understand if the surface is livable or habitable. And yeah, that's a really exciting period right now. I think we've discovered like 3,000 exoplanets.
And we have the Nancy Grace Roman Space Telescope, which is going to be discovering even more of
Right.
them. James Webb is still working on discovering more of them too. It's very excited time. For
Hopefully,
astronomy.
I've been talking to some astronomers, and like I think it's built already, but with all of the funding things going on, like people aren't even sure if it will fly. Like even though it's like built,
Yeah.
which is crazy.
Yeah, really. Yeah, it's an exciting time, but a scary time right now
Yeah.
for astronomy.
Yeah.
Yeah, we don't know what missions will end up being
Yeah.
followed through with. Okay, so we've gone from the Big Bang, the very beginning of everything, the rapid expansion of the entire universe, from a point that is the size of an atom to what it is now. After the Big Bang started beginning, we had the Dark Ages, where there's just that 21 centimeter line. The neutral hydrogen was the only light that was being emitted. And then all of the hydrogen in the universe, all of the matter in the universe started clumping together in areas and forming stars. We have the very first ignition of stars, the very first light that's ever truly emitted, lighting up the universe other than that 21 centimeter line. And those stars end up forming galaxies, and somehow we reach us.
And maybe galaxies form before stars. Like we're really not sure the order of that, and that's why, astrophysics is so interested in these very early redshifts.
So what do we still have yet to discover? You were saying that we don't know if galaxies or stars started first. We don't know where and how the first galaxies looked. What else do we still need to discover right now?
Yeah, yes. Essentially, at the very early universe, yeah, we had neutral hydrogen, but we also had these things called dark matter and dark energy. Dark energy, namely, being this weird force that expands the universe, accelerates its expansion, and dark matter sort of being the counteracting force on that. It's sort of pooling all this matter together. So the first galaxies essentially formed in these big reservoirs of dark matter, these halos of dark matter, it's called. And there's some observational signatures of dark matter, in the local universe. Something called the bullet cluster, where we've sort of been able to separate the gravitational matter from the visible matter. That's a really cool picture. You should look that up if you're listening. And yeah, so particle physics has been really interested in what dark matter is for the past few decades. But they haven't been able to find the particle of dark matter. They've been looking at all these different energy scales. And they've really just been narrowing down this parameter space of what dark matter could be. But they haven't been able to find that particle yet. And they might think that they have to get to these energies associated with the very early universe in order to actually figure that out. So it's a really uncertain time if we're going to figure out what exactly dark matter is.
There's a lot that we don't know about the universe, right? Dark
Absolutely.
matter and dark energy make up the majority
Of the energy,
universe.
Yeah, exactly.
And we also don't know what the fate of the universe will be, right? There's
Yeah.
multiple theories. Like it may just expand and then stop expanding so much that gravity is more powerful than the energy
Mm-hmm.
that's expanding the universe, so it might slingshot and snap back like a rubber band.
Big crunch, I think they
Yeah,
call that.
yeah. Or it can just cool out. It can continue to expand, and then as stars die out, they get recycled. But there may just be a point where all of the stars die and they don't have any matter left to recycle. They're just left behind these cores, and we have black holes, and everything in the universe is like basically the same temperature at that point. And then there's the Big Rip. that one's probably the scariest one to think about, where the acceleration of the universe just keeps going. Yeah, and it just keeps going so fast that even atoms, the distance between atoms starts to grow so rapidly and just goes off into infinity.
And maybe that's how new universes form,
Yeah.
like maybe that's what the multiverse is. Who knows?
Yeah, and like one of your professors said, the universe may just be inside of a black hole, and maybe there's other black holes out there.
That's the great thing about theoretical astrophysics. You don't need to know if you're right. You just need to come up with wacky theories and see if it intuitively makes sense.
Yes. So where can people go to figure out more about this topic?
There's various radio interferometry experiments that are trying to observe the cosmological 21 centimeter signal. There's a whole program called the Commercial Lunar Payload Services program that's sending scientific instruments to the moon and some of those instruments are trying to observe the signal. So one that I was a part of recently was called ROLSIS. One that's going to be launched in the next year is called Lucy Night. And those are all related to observing the 21 centimeter signal and preparing for these larger interferometers that might be built on the far side of the moon.
Viewers could look that up on Google or nasa.com. Thank you for listening, and we will be back with more voices from the edge of space science. Stay tuned.